Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Anne Limbach with us today. Hello, Anne.
Hi, how are you?
I'm doing awesome on this August 23rd of 2024 as we record this. And I am in Phoenix, and we are still in our summer. We're still up in the triple digits Fahrenheit. So we have a little bit more ways to go before we get into some of our fall weather. And how about you? What's your geolocation, Anne?
So I am in Ann Arbor, Michigan at the University of Michigan.
Cool.
That sounds terrible, actually. I'm sorry to hear about your weather. But I'm sure in the winter I'll be jealous. So
in the winter it's delicious. So, yes.
yeah, we this week it's gotten down to the 40s at night, and our trees have just a tinge of color on them. Just a couple of them. It's just like the very beginnings of the cool weather coming.
So. Midwestern falls are really nice. They're really lovely.
Yeah, it was great. 70s during the day, no complaints.
Oh, lovely.
Yes.
I'm jealous. I'm gonna have to get a summer home up there in Michigan or something like that. So it'll be good.
Yeah. Well, and me a winter home in Arizona.
Oh, well, maybe we can do house swaps. How about that? That's a thing these days, house swaps. So we can consider that. Very cool.
There you go.
Very nice. And Anne, what do you like to do for research?
So I do a couple of things. One of those is using JWST to search for white dwarf exoplanets.
Cool.
And the other thing is searching for exomoons and exosatellites around wide orbit exoplanets, free floating planets, and brown dwarfs.
Very cool. Very cool. Very nice. And that is going to bring us to this very awesome article on that topic. This is an AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Occurrence rates of exosatellites orbiting 3 to 30 MJup host from 44 Spitzer light curves. And Anne, take us away.
All right, thank you. So first, just a shout out to all my co-authors. Thank you so much for all your help putting this together. Certainly couldn't have done that without them. But yeah, so this paper, what we're doing here is we're leveraging the incredible archive of Spitzer data that was collected on wide orbit exoplanets, free floating planets, and low mass brown dwarfs. And we're taking those light curves and we're doing something that different from what they were collected for. So really, when Spitzer was looking at these objects, what it was trying to do is understand the weather on these worlds, which is an awesome thing to do. You can measure rotation rates, you can look at clouds coming in and out of view, and that's really quite fascinating. But it turns out that while you're looking at those light curves, if a satellite of one of these objects happens to pass between you and the object, you get a transit just like you would of an exoplanet of a star. And really, Spitzer turns out is incredibly sensitive to those. And so we decided to take those light curves and really see what we could find there.
Very nice. Very nice.
Yeah. Okay, so before I get into exactly what we did, a little bit of background. A good place to start. So we're in an interesting mass range, right? So 3 to 30 Jupiter masses. So a little bit more massive than Jupiter, but really significantly less massive than stars, where we would traditionally look for transiting companions.
Yeah.
And so it's hard to get like a good feel for this regime, but a good place to start is thinking about the moons in our own solar system. And so we know that they are quite abundant. So all the gas giants in our solar system have moons. There are 15 moons in our solar system, more massive than sort of 10 to the -6, the host mass. And so because of the abundance in our moon, or of moons in our own solar system, It seems reasonable that we might expect to find moons around planets and other systems, and perhaps free-floating planets as well.
Very cool.
And so there's been a lot of effort that's gone into searching for exomoons using a variety of methods. But this one, many times those methods are aimed at looking at the star and then trying to study maybe transits in the star that also have an additional transit.
Okay. Yeah.
And one might think this is a really good approach, and it is in many ways, because your stars are typically really bright. And so it seems reasonable that based on a signal to noise calculation, perhaps you could do this. And certainly there's a lot of good effort going into doing that. But what we're thinking here is just skipping the star altogether has some advantages. So if you just go straight for monitoring the light curve of the planet or the substellar world, you get the advantage of the host object being much smaller. And that means even though your signal to noise isn't as good, it doesn't need to be, because you can detect small objects with relatively large transits.
Okay, I'm with you. Good.
Yeah. And so there has been some effort put into sort of going in this direction. So surveys like Speculoos and Pines are ground-based surveys that have gone after transiting exosatellites or exoplanets around late M dwarfs and sort of higher mass brown dwarfs generally. So these observations are generally restricted to the higher mass objects because they're done from the ground. So this is a very interesting parameter space too, because we have a limited amount of detections around these lower mass stars and almost no detections around high mass brown dwarfs. But it's a very different parameter space than what we're talking about in this paper. And really, to probe into this 3 to 30 Jupiter mass range, you have to be doing it well into the infrared, which really means you need space. So these objects are faint, and for the sensitivity and stability that's required, you can't get away with doing this from the ground very easily. You really have to go. You need an infrared space telescope.
Yes.
Okay. Yeah, so I think that's a pretty nice summary of the background, or a background relevant to what we're doing here. There's certainly a lot of thoughts going into how to do this from the ground for those higher mass objects, and so doing it for the lower mass ones, though, infrared space telescope is the answer. And so with that in mind, until JWST, we had Spitzer. And Spitzer really did a great job of collecting these light curves, like I said before, to study weather. And it turns out that there was just a little bit of effort that went into searching these satellites or these light curves to look for transits. But when that was done, it was sort of under the assumption that these all were high mass brown dwarfs. And it was focused on sort of that portion of the sample, rather, and that study was done earlier on, before many of the light curves were collected. So with Spitzer's mission being complete, we now can go back and look at all the data that was collected, take those light curves, focus on that lower mass region that we're interested in, and really try to see what's there. So I will note briefly, as you're pointing to with your cursor there, that we did do this for just a couple light curves a couple years back. There we did see one possible exosatellite in the light curve of this 211 or this 1119 object. And that was sort of the motivating reason for why maybe we should do a more thorough search.
Excellent. Excellent.
Okay.
Now we got 32.
Yes, we have quite there. It's incredible how many Spitzer really did look at during its
Yeah.
mission. And I mean, 32, and each one by one, and most of these light curves are about a day in duration. And so really getting up there in terms of the amount of time Spitzer spent looking at these places.
Yeah, very good. Very
Yeah.
good. 1 to 32 is several, at least an order of magnitude.
Yes. Yeah.
Oh, okay.
Okay.
Well, maybe.
So this talks about the sample, but I think with regards to the sample, maybe we're best looking at the table
Okay.
and
Let's
talking
take a
about it that way. Yeah.
Yep.
Okay. So this is the sample of objects that we have within our survey. We did a cut on mass at 30 Jupiter masses. So anything that had a mass above that, we excluded from the survey.
Okay.
I'll get to why that is in just a minute.
Mm-hmm.
So these objects, there's a few interesting things about them. So generally, if we want to study the light curves of low mass objects, they need to be young. Because these objects are not fusing, they cool with time. And so we can catch them when they're young. They're still bright from that heat left over from formation.
Yes.
And that means because they're bright, we can get enough photons to get a reasonable signal to noise when we're doing the monitoring. And so if you think about, searching for transits around exoplanets, we're usually thinking of very stable middle-aged stars that have nothing notable going on. And it's quite the opposite here.
Oh, yeah.
So we know of very few exoplanets that are extremely young. Because those stellar light curves are highly variable, and so it's a hard place to find exoplanets. Well, it's the same here. The light curves are very variable at a young age. In fact, they're variable their whole lives. But that's just not something you can get around. And so we go for the young ones because that's where the high signal to noise is. And so as you can see, these objects are often tens of millions of years old. Instead of giga years old, as is the typical age of our exoplanet hosting star.
You got some really fun ones here too. You got a couple of 10.
Yes.
Yeah.
And the ages generally are the way we know those is these objects are generally associated with a young moving group, and we pull the age based on that association.
Moving group. Yep. I'm with you. Yep.
Yeah. Okay, and they're all near fairly close by, so generally 10, 20, maybe 30, 40 parsecs.
Whoops.
Okay. And then you can see on that mass column, you have those light curves going, or those masses going down to about 3 Jupiter masses and then up to 30. A nice range there. I think the median value was about 16 Jupiter masses, so right in the middle of the range we were targeting.
Right.
You can see the light curve durations, often about 20 hours of monitoring time, sometimes a bit more, sometimes a bit less. There you're looking at, there's 2 main bands that we do the observations with, or that was done with Spitzer. So those, that's the IRAC band 1 and 2, so 3.6 microns and 4.5 microns.
Gotcha.
Cool. Yeah.
Yep.
Okay. So that's, and they're all L&T dwarfs for the most part. There's yes.
Yeah.
So, yeah, I think that's pretty much the main takeaway. There is a few exoplanets on this list. So Ross 458c specifically. So and then some higher mass objects that are bound to a star, like HN Peg B down there a little bit further. So that one's a brown dwarf, but it is bound to a star. And so it although most of our objects are sort of in that free floating planetary mass object range, there are, a few exoplanets that are in there as well. So this isn't just exosatellite hunting, which is the term we're using for things that are free floating. It is also exomoon hunting, which is the term we're using for things that orbit a planet that are bound to a star.
Okay, good.
Okay. So right, back to why we cut the mass off at 30 Jupiter masses, which for that we need figure 1.
Let's go to figure 1. Okay, transit probabilities.
So So one reason we cut the mass off at 30 Jupiter masses is we are really interested in things that are more moon-like than planet-like. But the other reason is it turns out that that low mass region is actually where we have a much higher probability of detecting transits, believe it or not. So this is somewhat counterintuitive. You would think you want higher mass objects because they would be brighter, and then you would be able to get to lower, or to smaller satellites. But
Yes.
that actually, it doesn't actually work out that way
Huh?
when you run the numbers.
Yeah.
And so there's a few reasons that is. And one is just transit probability. So if you think about Io around Jupiter,
Okay.
Io actually has a transit probability of almost 20%, assuming a random viewing angle. So very high. That means if you just chose 5 Jupiters out in space and they all had an Io, one of them should have an Io that's transiting.
Gotcha. Okay.
And so when you think about that relative to exoplanets, typically you need like thousands of stars in your sample before you start finding one transiting exoplanet.
Yeah.
But for moons, we don't think that's going to be the case. We think it's going to take a much smaller sample before we start finding a system oriented with such that transits can occur and hosting satellites that do transit. And the reason being, not only are the transit probabilities high, but unlike stars, we also think occurrence rates of short orbit moons and satellites should be high as well.
Got it. Very good.
Okay.
Okay. I love
so,
the EO analogy. Very nice.
Yes.
Good.
Okay, so the takeaway from this plot is as we go to lower masses, the transit probability increases for an exosatellite on a one-day orbit. And as you're reaching those very low mass objects, you're talking about transit probabilities of up to 20%. So that even though we have a sample that's 32 objects, we have a reasonable probability of something transiting if the occurrence rate in the parameter space we're sensitive to is high enough.
Yes. Yes.
Okay.
Good.
So
okay.
That's the takeaway there. And then we'll scroll on down to figure 2.
Figure 2, which is going to be durations.
Yeah, so we're getting close to where we're going to start talking about transit searches. But before we do that, it's good to think about what duration of transits we're expecting to find. So we can ask this for our target list. And we see a few things here. So we see this is for edge on. So assuming that you have exactly edge on inclination viewing angle of your system. And here you see transit probability or transit durations going from about 40 minutes up to a couple hours. Now, if they're not edge on, it can drop below that. So when we're searching for transits, we generally use a prior that goes from about 20 minutes out to 2 hours.
Okay.
We cut that lower limit both because we're not sensitive to those short period transits, but also because we don't expect there to be that many in that range. And so we're only losing sensitivity of those grazing transits anyway, and we wouldn't be able to detect them. So really no, very little is lost.
Okay, very good. That's a good long transit duration. Okay.
Yeah. So what's interesting here again is you'll note that transit duration going up as you go to the lower masses. And this is another reason why it actually helps to look at low mass objects. So you would think, again, you would have higher signal to noise on the more massive, brighter objects, but that's sort of canceled out by the fact that you get a longer duration transit for the lower mass ones, which gives you more signal since your transit is longer and helps you with the detection.
Very good. Very good. Okay, I'm with you.
All right. So we're going to do a few things in this paper. First, we're going to look and see if there's any transits.
Okay.
Then we're going to do an injection and retrieval test to find sort of what our sensitivity is in the parameter space of detecting transits, and then use that information combined to say something about occurrence rates.
Very good. Okay. Cool.
So if you scroll up just a little bit,
yeah,
there we go. So when we're searching for transits, we're using a GP plus transit model. So
Nice.
the GP is a quasi-periodic kernel, and basically it's just used to capture variability. So we really don't care what the variability is doing. We just care that we're modeling it and getting rid of it.
Okay.
And then we add a very simple transit model to that. So it's just a trapezoid. We don't do any limb darkening because we do not have high enough signal to noise that it matters.
Okay.
And so all this is a GP plus transit fit. And so we're using that model to search for transits within the light curve. And then what we also do is we use a GP only model. So it's the same GP model, but no transit included.
Okay.
And then comparing the goodness of fit between those two enables us to say which one's favored and therefore choose if there is a transit or not.
Cool.
Okay. So let's go on to the next figure.
And figure 2, and let's go on to results, figure 3, probabilities. Okay.
Yes. Okay. So the first thing we needed is a control sample. So how do we get a control sample? Well, the way we did this is we flipped all our light curves upside down. So transits only occur in one direction. And so if you flip all your light curves upside down, you can't have any transits, and anything that looks like a transit has to be variability.
Yeah.
And so by flipping everything upside down, it tells us the extent to which things, variability can emulate transits.
Yeah, very good. I love it. Very good. Okay.
So we start with this flip sample, and we run our GP plus transit code, and we run our GP only code, and then we do the delta log Z of both of those fits, and we get this lovely distribution. And then we fit a normal distribution to that. And this is what that looks like there on the left. And so as you can see, so the negative values favor GP only, and the positive values favor GP plus transit. So we expect more positive values if the transit is favored.
Okay.
So for that, for our control case for our flip light curves, you do see that generally the GP only model is favored, which is good.
Okay.
It should be. You can sort of see based on that, the width of that distribution, the extent to which variability can sort of look like transits.
Yeah.
So there is some cases where we get a little bit of a tail there going up on the left-hand side to above 0. So, you know, very marginal in the noise saying, you know, GP plus transit maybe. So that tells us sort of, okay, this is the level at which we expect variability to look like a transit in this set of light curves. Okay. So we then, based on that, the normal distribution fit we make to that delta log Z distribution, define what is a 2 and 3 sigma detection of a transit. Okay. Now we're ready to actually look for transits. So in our unflipped light curves, we now do the same test. We make the same distribution of delta log Z's. And here we find something very frustrating, which is that, so the two answers that you want when you're doing data analysis is the two clear-cut answers, which there's absolutely nothing, or there's clearly something. That's the answer you would like. But this is, of course, neither of those answers, which is really not what you want. It's quite frustrating. So what we found was the distribution looks relatively similar, except there's just a few things that popped up on the right-hand side that seem like they could maybe be something.
Yeah.
But it's at this level where it's like, so at the highest end, we're looking at things that are almost 3 sigma. It's sort of at this level where you're like, okay, what do I do with these? Because, you know, if there wasn't anything there, then it's easy to say, okay, our occurrence rates based on non-detections are this, or follow up something if there is. But with these marginal detections, it becomes challenging. And so based on this, we did a few things from here. We took a look at what these outliers look like. We sort of tried to understand if we were capable of detecting transits that were similar to these outliers. And then we sort of decided to derive occurrence rates, assuming in the case that none of these were real,
Okay.
and
Okay.
in the case that maybe one or two of them were.
Okay.
And then that can sort of give us an understanding of what may be going on here.
All right. Yeah. Okay.
Okay. All right. So the first thing was to take a look at these light curves. So we'll take a look at the two most anomalous outliers here. So if you scroll on down, oh, it's actually worth stopping here. So this list here, 1, 2, 3.
Yes.
So we note that these are the three explanations for the outliers. So it's random chance it has a 2.2% probability of giving us that many outliers. And then it might be that they are transits and they're just at that marginal detection level.
Right.
And then the third option is that we have host variability that's asymmetric.
Yes.
So our control sample, by definition, we're assuming that sort of variability looks the same. If flux increases and decreases look the same due to variability. But if that's not the case, then maybe we could get some bias.
Yeah. Okay.
Okay. So that's certainly relevant. Okay, now we can go on.
Yes. Okay. Good.
All right. So this was the light curve that had the highest sigma detection of a transiting satellite-like signal. So this is 2117, 2-mass 2117. It's a 7 Jupiter mass planet, free-floating object. The transit that the code picks up on here has a depth of about 0.3%. So we're talking about something, once you work out that size, that's sort of halfway in between Mars and Earth. So pretty small, getting in there. Certainly, if you're thinking about sort of mass ratios, it's quite small, given that this is a 7 Jupiter mass thing. So not far from your sort of Titan to Saturn mass ratio.
Yes. Yeah.
And then if you very crudely try to estimate what the orbital period of this might be based on the slope of the ingress and egress,
yes,
you get something of order a day and a half. So not crazy. Not crazy. So there's a few interesting things about this light curve. So there's a lot of variability. And that variability, it has amplitudes that aren't that different from the actual depth of the transit. But what's interesting is that variability does seem to have a very different frequency than the duration of the transit that the code's picking up. And so that I think is interesting. We do see a lot of false positives where we have more information with more recent JWST data sets. We do see a lot of false positives where there is sort of transit signals that are showing up at the same frequency as the variability. And so the absence of that, I think, helps. But at the end of the day, this is a 2.7 sigma detection. And so it's hard to say if what we're looking at is just, noise, variability, or maybe something that's more interesting.
Right.
This is certainly, I think, the system, if I was to pick any out of these papers, out of this paper, that is worth following up. I think it's, there's some chance, it's hard to say what that is, that this could be due to an actual exosatellite.
Well, it's the best one yet, so.
So hopefully that's something we're able to do someday.
Let's look. Okay.
Yes. It's hard because following it up, we don't know when to look for the signal, since there's only one event that occurred many years ago. And so you have to monitor it for, what you think is the entire orbital period. So a day, at least a day and a half. And that's a lot of time when you're not sure if there's something there. Yes.
Okay.
All right.
Max, do your thing.
All right, so we can look at the next light curve too. This This is that one I mentioned at the beginning of the paper
Mm,
that we actually saw a few years back and sort of motivated this more detailed search.
yes.
This one is a much larger satellite, so it's sort of at that large terrestrial cutoff. It's like 1.6 Earth radii. And this light
Okay.
curve,
Uh,
so this one's actually a binary. It's three Jupiter mass objects that are on a 3 AU orbit about each other.
okay.
But if this was a satellite, it would be extremely short orbit. So
Okay.
I mean, there's no dynamical, issues with having a satellite here.
Yeah. Just
Orbiting
mass
one of those two.
Yeah. Yeah.
Yeah, yes, it would be orbiting one of those two objects on a very,
So
very
really,
short
it's
sort of
like,
one
yeah,
day.
must be
Yeah. But this one, I think,
curious.
it's it's more suspect because the signal in this case sort of is at that same maybe the same frequency we're seeing some variability at.
Mm,
But nonetheless, it's not
yeah.
completely implausible that maybe that's something that's transit like. And so
Mhm.
um, perhaps someday this is something we'll get to follow up to. It is good to see. So we're using a slightly more updated version when we're searching for transits and using a much more systematic method than what we had used previously. And this certainly still does pop out as, one of the best two candidates.
Yeah.
So it was good to see that signal that we had
Oh, yeah.
flagged early on was indeed anomalous in terms of what is typical in terms of deviations we see in these light
Yeah.
curves.
Yeah. Anomaly detection. Mhm. Cool.
Yeah.
Okay.
Yeah. So those are the two most interesting outliers
Okay.
that we saw.
Right. Still not been out there. Yep. Hmm.
Yeah. Um, And so the next thing we wanted to ask was, okay, so this is the type of signal we're detecting. Um, and like generally in this sample of objects, if we inject and try to recover light curves that look, or sorry, transits that look similar to the ones we found, are we capable of doing that?
Even getting.
Because if we're not, then these probably aren't real.
Right. Yeah. This is
Yeah.
an important test to do. Hmm.
Yes, and also, of course, this is an occurrence rate paper, and so if we want to say something about occurrence rates, then we need to do a very thorough injection and recovery testing.
Right.
Um, okay, so we set off to do that, and we tried to cover the range of durations and depths that were relevant both to the signals that we had potentially detected, as well as the full range of signals that um, a large enough range of signals that we could say something about occurrence rates. So we tried to get all the way down to the floor where we weren't really detecting anything anymore to find the limit of what we were sensitive to. And then as well as much larger transits, so we could say something strong about sort of sub-Neptune occurrence rates, which we don't expect there to be sub-Neptunes in this sample because the host mass are so low, but since we can say something strong about them, we should.
May as well. Mm-hmm.
Yeah. Okay. So if you scroll down just a little bit, the next figure.
Figure 6.
Yeah. Okay. So what this is showing is the number of percentage of recovered transits as a function of the brightness of the host.
Yes.
Okay. So, and then the injected transit depth there is the different types of lines. And so you can see for those small transits, those 0.3% transits, the recovery rate is much lower than it is for 1% transits, which is nearing 100%.
Oh yeah, it's a solid line up here. Yep.
Yeah. And so we're really not very good at detecting things much smaller than 0.3%. We're very good at detecting things that are 1% transits. And then the stars on here are those three objects that were outliers in the earlier plot where we were looking at the delta log Z distribution.
Yes.
And so what we're showing there
Okay.
is the percentage of similar objects that we were able to recover.
Got it.
And so in those three cases, you can see we're sort of recovering between about 40 and 90% of things that are similar. So it's good that that's not zero, or
Yes.
close to it, because that would suggest that there's something anomalous about other detections we make, because we're really generally not capable of finding things that look like that.
Yeah.
So it sort of seems like in some cases we do find things that we injected that are that small. And so it's certainly plausible that if those are
Okay.
transits, they could be detected.
They're not ruled out.
Yeah. And so that certainly, doesn't show that they're real, but it doesn't show that they're not real. Okay.
Cool.
So what was also really interesting, this is a little bit of a side note, but I think it's just interesting generally, is if you go over to figure 7 really quick, it turns out in our sample that
Okay.
part of the sample, the bright portion, was variability limited. So that's that blue line up top. And then the fainter part of the sample was actually signal to noise limited. So what we see is this very interesting thing where for those bright ones where we're variability limited, we actually do better for the shorter orbital periods, which have very short transits. And the reason for that is because short transits are very far away from the frequencies we typically get due to variability.
Yeah. Okay. Good.
And so we're very good at recovering short transits when we have plenty of signal to noise.
There you go.
It looks very different from variability. And so getting more signal in those bright cases actually hurts, because it just turns out that that means longer transit durations, which looks like variability. And so your recovery rate goes down.
Yes.
The opposite is true for the faint ones where we're signal to noise limited. So getting a longer transit actually helps. And you recover more as you move to those longer orbital periods. So as a whole, it turned out that we were actually relatively uniformly sensitive to all orbital periods prior to taking into account transit probabilities as a function of, how long we observed and all of that. But in terms of just injection recovery, it was pretty flat across the board, which is really quite fascinating once you start looking into the reason why that was.
Yeah, that was really good. That was good explanation. Good. Okay.
Okay. Okay, so I think we can skip the next figure and go on to the first occurrence rate figure.
Okay.
So based on our injection recovery test, we tried to say something about occurrence rates of exosatellites around these substellar worlds. So first we did this assuming that none of those outliers were true transits, which could very well be the case. We did this in sort of 4 bins. So the left side is very short orbit, so 0.8 day and shorter. And that 0.8 day is sort of the typical duration of the light curves we're looking at. So that's why we chose that. And then we did it for slightly longer orbital periods there on the right as well, going out to about a day and a half. And then we did it for sub-Neptunes and terrestrials.
I'm with you. Yep.
So for the sub-Neptune, so I should say that all of those outlier signals that we did detect were consistent with terrestrial worlds, not sub-Neptunes. And the sub-Neptunes, our recovery rate is nearly 100%. And so if there is anything there that was a sub-Neptune, like we would have seen it by eye, no problem. Like it would have been very obvious. And there was not. And so I think that our sub-Neptune like constraints are very strong there on those top panels. And we can say with strong certainty that the occurrence rate is sort of at the less than 0.3-ish exosatellites or sub-Neptunes per substellar world. Which is expected. So we really don't expect, as I mentioned earlier, sub-Neptunes to be forming around substellar objects of this mass because they're so low mass that mass ratio of a sub-Neptune to substellar object would be quite high compared to what we usually see for companion formation in a disk.
Okay.
All right. But for the terrestrial satellites, that's not true. So based on the sensitivity we got in our injection recovery test, we're just raising that limit of what we would expect the occurrence rate to really start tipping up in terms of what we see, both in terms of like companion to host mass ratios in our own solar system for like the gas giants and their moons, but also for what we see for those late M dwarfs and the occurrence rates of exosatellites around those, and sort of looking at the orbital periods and host mass to companion mass ratios for those two populations and formation theory. It's basically Spitzer's just raising the top of what we would expect, you know, those formation rates to start kicking up.
Cool.
And for our solar system, there's sort of one or two satellites that are close to the same mass ratio and orbital period that we're probing with Spitzer here to give you an idea. So you're looking at sort of maybe a quarter to a half of exosatellite per gas giant in our solar system. That's in this terrestrial satellite sort of same parameter space.
Yes.
Just for comparison. Okay. So what the takeaway there is because for the terrestrial satellites, we're saying the occurrence rate is less than maybe a half for those short orbital period ones, or more than that for the longer period ones. We're sort of getting in the regime where we actually might start expecting to find something. So you can ask the question, if the occurrence rate is the same as the solar system gas giant moons, should have we found something? And we're right on the border where we might have, if you assume a similar
getting closer
occurrence rate. And so that's really exciting because it says that we're starting to finally say something exciting and interesting about the occurrence rates of exosatellites around stellar objects with this data set.
Very cool.
Okay. So the next thing we did, you can scroll on down to that next
let's go down to 10.
plot. Yeah. And so then we said, okay, well, what if one of those transits was real? And one or two of them were real, then what is the occurrence rate we get? And then we're getting something that's like 0.6 plus or minus 0.3-ish exosatellites per substellar world. And so actually, that's not crazy. It's possible that for the orbital periods that we're probing, that could be the answer. It's not it sort of agrees with what we see for the solar system gas giant moons and as well as late M dwarf exoplanets.
Right.
And so interesting.
Yeah, it's not grossly out of bounds.
Right. Yeah. So I think
good.
That's sort of where we end. So we sort of end with noting that it's certainly a plausible answer if it turns out someday to be that one of those satellites was indeed, or one of those transits was indeed due to a satellite and not a transit that looked like a transit but was actually variability.
Cool. Very good.
Yeah.
And I suspect we'll come back in here in a minute. So very good. I think maybe we'll save that one for a little bit.
Yeah.
Do you want to save it for a minute or so?
Yeah, we can come back to that one and sort of talk about where we're going next in a minute. Yeah.
So we'll do a little bounce in and out. So Marianne, I want to thank you so much for walking us through this awesome hunt for exosatellites. I think that would be pretty darn cool. Very good. And so you kind of hinted at it a little bit there at various points when you went through. And so I'll push on it, and we're going to take a look at it here in a sec. But what are sort of the next steps as we go through here? Is there a possibility of getting 330 exoplanet candidates. There are other wavelengths that we can look at as there are new missions going up that might have instruments in the proper wavelength range to take a look at, and so on. So where do you think we go from here?
Yeah, so for those of you who haven't heard, sadly, Spitzer was decommissioned, so no more Spitzer data.
Right.
But great news, there's a new infrared observatory in the sky. So JWST is capable of monitoring these worlds, and with, of course, much higher precision than we were able to achieve with Spitzer, and over a much broader spectral band. And so, yeah, I think, and not only that, but actually Roman is going to be able to do great things too for this field, this subfield in the coming years. And so, yeah, if we want to take a look at that last figure, pump it back up, we can talk more specifically about what I think should be possible there.
This is an figure. Okay.
Okay. So what we were trying to do with this last figure is think a little bit about the parameter space, like we as a field have probed so far, and like where we're trying to go. And so what's really remarkable when you look at this plot is the known exoplanets actually fill a very small region. So they're all up there around solar-ish mass stars. You know, give or take some, but not a lot. And if you look at where Jupiter and its satellites are relative to this, there's just this huge parameter space where we have so much to learn about. And there's a couple surveys that have tried to probe this space, but in many cases, we have very limited sensitivity or very limited number of sources in these surveys, and as is the case in this paper I just talked about. And so that sort of limits our ability to make detections. But it turns out that JWST is doing the exact same thing Spitzer did, which is it's going and looking at wide orbit exoplanets, free-floating planets, and substellar worlds, and it's studying their weather. And now it's doing it spectroscopically resolved. So we're getting these spectrophotometric light curves from JWST of more than a dozen worlds over the course of cycles 1 through 3. And while designed to look for weather in the same way these Spitzer light curves were, they're fantastic for searching for moons.
Yes.
And what's really incredible is not only are we getting more sensitivity, but because the spectral information there is there as well, we now have the ability to leverage that information and differentiate between variability and weather, which is chromatic, and your transits, which are achromatic. And that's getting us down to things smaller than Europa in the JWST light curves. And so I'm really excited about what's coming there. I think we've shown previously that JWST should have this capability, and with recent data, it's looking like it's actually achieving it. So more to come there soon. And then just I'll briefly say Roman too, it's got a couple more years here before it's probably producing data, but
future.
Yes, it has the advantage. So obviously not quite the sensitivity or the spectral coverage of JWST, but the field of view. And so you can point Roman at something like the ONC, capture hundreds of free-floating planets and substellar worlds simultaneously, and get much longer duration, so maybe 30-day light curves of hundreds of these worlds, allowing you to do a broad search.
Nice. Very cool.
Yeah. So all exciting things that we're hoping will come in the future.
Yeah. I would say the future is bright and exciting going on. And it'll be really cool to see this develop over the next couple of years. As JWST stuff comes on and Roman fires up, it's going to be really great over the next couple of years. And someday we will find some.
They have to be out there.
They have to be out there. It's just a matter of looking. So we'll get it. It's very cool.
Yeah.
Mary Ann, thank you so much once again for walking us through your very lovely article.
Yeah, that was great. Thank you. Thank you for having me. I much appreciate it.
Yep. And everyone, I hope this made your astronomy day just a little bit better, and I'll see you on the next one. Bye-bye.